Okay, now we're going to look at in the last video, we looked at the real case. In this video, we're going to look at the complex case. Now, just as in the discrete case, the continuous case, complex values are also going to generate rotations. And if they're completely complex, they're completely imaginary, then you will get stable orbits. If there is any real part to the expression, then for real world problems, they will spiral in toward the origin. How quickly that happens is going to depend on the size of your exponential component, that real piece. In real world problems, they do not spiral out. Although in the general in the general complex case, outside of this sort of real world cases, you could conceivably get outward spirals. But typically we set these up and we think of them, we solve them in terms of, let's say, typical first order real world problems. They will spiral into zero, not out to infinity. Now, complex trajectories, again, they will be spiral-like, depending on how quickly they spiral into the origin. They could be very quickly coming in, or they could be spiraling in very slowly. Real-world problems will tend to curve a little bit, but they will tend to sort of curve in the direction of the eigenvalues. And so the ones that are further away will curve a bit more. The ones that are closer to the eigenvectors will tend to just go straight away or straight in. And then, of course, the saddle trajectory that we saw in the previous video. So you can think of this as the attractor graph, everything's going in. This is the repeller graph, everything is going away. This is the saddle point graph, similar to the previous video. And then something like this would be more like what you'd expect with complex solutions. Although in this particular case, they are spiraling outward. Now, we want to look at an example of the complex case and how that would differ from the real case. And there is a little bit more algebra involved, although the general outline is going to be quite similar. Here, rather than write my differential equations in the derivative x1 over dt and the derivative x2 by dt, and then write it out all the equations, I've simply started in this case in matrix form, because always we're going to have to put it in this form and then work from the matrix form to find our eigenvalues and eigenvectors and so on. So we've got it in this form. To find the characteristic equation, remember, we subtract lambda off the diagonal, and then we find the determinant. So this becomes -7 minus lambda times 5 minus lambda, and then minus this off diagonal, which gives me, since it's already negative, a plus 40. And foiling this out, we end up with this expression. This does not factor. There are no factors of 5 which have that sum to 2. So we're going to use our quadratic formula, and we end up with a complex solution. Now, we already know that the real part being negative means it's going to spiral in, which is, again, what we'd expect from, let's say, a spring problem or something like that. But we have this complex piece that we're going to have to deal with. Now, to start with, we're going to have to find our eigenvectors more or less the same way. We're going to subtract our eigenvalue off the diagonal, but our coefficients are going to be complex. Now, when we subtract -1 plus 2i off the diagonal, then you get -6 minus 2i and 5 minus a -1 plus 2i in parentheses. You end up here. Now, this is very common for these kinds of matrices where the diagonal elements now look kind of like each other, but the sign change is in the real part. You can verify algebraically that these are multiples of each other, you would need to multiply by a complex value in order to get this complex to rescale to a real value. But it is algebraically doable, and I'm not going to demonstrate it here, but it is algebraically possible to demonstrate that these are in fact multiples of each other. They're just complex multiples of each other. So take one of the equations. I typically choose the one that does not require me to divide by a complex number, which is the bottom one, and create our system of equations. So this is negative 4x1 plus 6 minus 2i x2. I move my 6 minus 2i x2 to the other side of the equation. And then when x2 is free, I divide by my negative 4, and I end up with this expression. Now, I'm going to in order to get rid of the fractions, I'm going to let x2 be 2. And my numerator then will become my x1. Now, one advantage of complex values is that the roots are complex conjugates of each other. And if you redo all of this algebra, the only thing that's going to change is the sign of the two i's here. And so your vectors are also complex conjugates of each other. So you don't actually have to find it the second time. Even though this can be a little bit messy to find it the first time, you save yourself some work by not having to do it twice. Now, what we end up with, if we follow our general formula, is that we have a complex vector times a complex exponential. And we can't really leave it like this. We need real solutions. We can't plot these in graphs if they're complex. So we have a bit more algebra to do once we get it to this form. And we only really have to work with one of the solutions because we're going to get a real part and a complex part. And we can get another real part by letting one of the coefficients be complex itself. So we're just going to work with one of these vector root combinations, vector eigenvalue combinations, and then that will get us actually our entire solution. But we do have to do some work here. So first, we're going to apply exponential rules to separate out our exponential piece into a real part and a complex part. The e to the negative t is just going to be out there. So we're going to come back to that later. The complex part, though, we're going to rewrite using Euler's formula. And so that theta is going to be our 2i. And again, remember the theta will actually be 2t because the I is out here. So what we end up with is the e to the 2it becomes cosine 2t and I sine 2t. Then we're going to have to take this expression for the exponential piece, and we're going to have to multiply it through our vector in order to separate out our real and our complex terms. So 3 times this whole thing. Again, I pulled the e to the negative t out because it doesn't really do anything. It doesn't interact with the complex parts here. And then minus I times both of these. And minus I times I is going to give you minus a minus 1, which is going to give you a positive sine 2t. And then also through the denominator, the 2's. And then we're going to pull out the real parts, this part and this part, and this part to be in the bottom. And then in the complex parts, we're going to pull out this complex part and this complex part, and then this complex part. Pull the i's out front. And then when we rewrite our expression, the real part will become one solution. So e to the negative t times this piece we had here. And then we let C2 sort of absorb this I constant to make it real. And then this is our second form of the solution. So messy, but we get a real answer in the end. And you can't skip these algebra steps. You have to go through and do the work to get there. Now, once we have this thing, then we can plot things. So we can choose examples for C1 and C2, so A and B. And then, again, extract X1 and X2. So in our parameters x and y from our equation. So e to the negative t times 3 cosine 2t, we can, now the 3's here are going to be important because they're going to rescale this constant from these two equations. So once you pull these out, you can't actually absorb them into the constant because they have to be scaled in a particular way relative to each other. So you're going to have to keep that C1 in this case as A, and then 3 cosine 2t and e to the negative t sine 2t. And then again, your x second constant, e to the negative t 3 sine 2t minus cosine 2t. So it's very long, but you do have to keep these scaling factors in there because they matter. And then your second equation is a little shorter, but you pull out your unknown constant, e to the negative t 2 cosine 2t, and then your second unknown, e to the negative t 2 sine 2t from here. And then there are no real eigenvectors to plot, so we don't have to worry about plotting those lines. And then with different initial conditions, you will see that this will spiral in your calculator. You can change how long t runs, but because this is going to spiral in relatively quickly, you're not going to see very many rotations going around the origin, but you could zoom in, zoom around the origin, and then you can see, so you would see this outer thing, and then you would zoom in and you would see a little bit more, and then you would zoom in and you would see a little bit more, but it's going to go to the origin very, very quickly. But it's that spiral behavior that we would expect from the complex solutions.